Welcome back. Section 7.1 is on eigenvalues and eigenvectors. Definition. Let V L from V to V, notice the same vector space, be a linear transformation of an n-dimensional vector space V into itself. The number lambda is called an eigenvalue of L if there exists a non-zero vector x in a V such that Lx equals lambda x. What this means is x, image of x, is some number times x back. Such a lambda is called eigenvalue and such an x is called eigenvector. Okay? That non-zero vector x is called eigenvector of L associated with the eigenvalue lambda. Notice this may seem a weird definition, but very soon you will get used to what these mean. So I repeat, let L be from a vector space V to itself. It is a linear transformation. Number lambda is called eigenvalue of L if there exists a non-zero vector x in V such that Lx equals lambda x. Such a non-zero vector x is called an eigenvector of L associated with the eigenvalue lambda. So for eigenvalue to exist, eigenvector must exist. Okay? Now, eigenvalues are also called proper values, characteristic values, latent values. Okay? Depends on the author. Our author uses the term eigenvalue, but some authors call them proper values, characteristic values, latent values. Likewise, eigenvectors can also be called proper vectors, characteristic vectors, or latent vectors. These are just different terminologies. Remark. Eigenvalues can be non-real complex numbers. Eigenvectors could have non-real imaginary components. Let's look at an example. Suppose my function L is from R2 to R2. So linear transformation, which takes x1, x2 gives you x1 negative x2. So remember, this is reflection about the x-axis. Second coordinate changes sign. Alright, I want L of x1, x2 to be lambda times x1, x2. I'm looking for an eigenvalue. L of a vector must be lambda times the same vector. Let's see, can we think of some examples? L of x1, x2 is x1 negative x2. This has to be equals lambda x1, lambda x2, which means lambda x1 has to be x1 and lambda x2 has to be negative x2. One case, take lambda equals 1. If lambda equals 1, that satisfies x1 equals x2. But this doesn't satisfy unless x2 is 0. So x1 equals can be anything, x2 has to be 0. Then lambda equals 1 is an eigenvalue and this is the corresponding eigenvector. Another case, lambda equals negative 1, in which case this will be satisfied, but this will be satisfied if x1 is 0. x1 is 0, lambda equals negative 1, that's an eigenvalue, and the corresponding eigenvector is when x1 is 0. So you see, you got two different eigenvalues and two different linearly independent eigenvectors. Okay, let's look at another example. LB linear transformation defined by vector AB goes to vector BA. That is, I'm flipping A and B. Okay. Now, vector AB, L of vector AB should be lambda times vector AB. That's what it means to be an eigenvalue. L of a vector is lambda times the same vector. What does this mean? L of AB is BA. So BA is lambda times AB. This implies one case when lambda is 1, B equals A equals B. So A equals B. So eigenvalue equals 1. Your vector is AA. Eigenvector is AA. On the other hand, what if lambda is negative 1? Then B is negative A is negative B. That is their opposites. So when eigenvalue is negative 1, eigenvector is A and B are opposites. So A, negative A. You see? So here is another example, right? Let's look at another example. Remember the counterclockwise rotation given by this matrix. When you multiply by this matrix to vector xy, the result is a vector that is rotated by angle theta. Now you know about rotation. When you take rotation of pi radians or 180 degrees, you take an angle a vector gets mapped to its opposite because 180 degrees takes a vector to its opposite. In other words, lambda is negative 1. For this eigenvalue, you get every vector gets mapped to its opposite. On the other hand, when you don't rotate at all, then L of xy is xy, that is lambda is positive 1. So negative 1 and positive 1 are two different eigenvalues. Okay. Here is yet another example. So notice this section is full of examples. We will see how we are able to guess these lambdas shortly. Let's look at L from R2 to R2. So that is row space. x1, x2 goes to 0, x2. That is x1 completely disappears. Now notice L of x1 0 is 0, 0. Right? 0, 0 is nothing but 0 times x1 0. In other words, x1 0 gets repeated for lambda equals 0. So that's an eigenvalue. Eigenvalue 0. Eigenvector is x1 0. What about eigenvalue equals 1? L of 0 x2 will be 0 x2 because x1 becomes 0 anyway. So 0 becomes 0. So when lambda is 1, 0 x2 is an eigenvector. Alright, let's look at another example. Let V be the vector space of all real valued functions which have derivatives of all orders. Suppose L is from V to V defined by derivative of the function f. You want L of f to be lambda times f. So for some number lambda, L of f to be lambda times f. Now you may have seen something like this in differential equations course if you have taken it. If you have not taken it, let's look at it now. What is L of f? It is derivative. Derivative is lambda times f. How do you write derivative? It is dfx over dx. df dx is lambda times f. This is called a separable equation. You see, I can bring the f down and dx up. So df over f equals lambda dx. Integrate both sides. When you integrate the left, you get natural log of absolute value of x. When you integrate the right, you get lambda times x plus some constant of integration. To get rid of natural log, what do? Raise it as exponential of e. So fx is e to the right hand side. E to c1 times e to lambda x. You see, because of that plus, it becomes e to c1 times e to the lambda x, which means fx is e to c1 is a constant c, e to lambda x, that is your function f. So this is an eigenvector for eigenvalue lambda. For every eigenvalue lambda, eigenvectors look like this. Okay, in this particular example. Let's look at another example. L be a linear operator from P2 to P2. Remember P2? Degree 2 or less polynomials. So what is the operator? I have defined it as L of AT squared plus BT plus C equals negative BT negative 2C. So you see degree 2 is missing. So I'm actually landing in degree 1. Left hand side, take as bases 1 minus t, 1 plus t and t squared. Right hand side, take bases t minus 1 t and t squared. You have two ordered bases. Identify matrix A that represents L in terms of these two ordered bases. L of 1 minus t. So you see I'm looking at vectors from the left. By this formula, L of 1 minus t is nothing but negative t plus 1. By this formula, I get t minus 2. What is t minus 2? It is 2 times t minus 1 minus 1 times t and 0 t squared. So L of 1 minus t in terms of t, this is the coordinate vector. Likewise L of 1 plus 2, so 1 plus t, I get a coordinate vector. Likewise L of t squared, I get coordinate vector. Take these three coordinate vectors, that's your A. Okay. 1 minus t in terms of the right hand side is this. You multiply by A, you get the left. Okay. So we may check this. There is nothing here to check that we haven't seen before. Okay. Notice we have built L of V with respect to we could have built. So you see, instead of taking two different ordered bases S and T, we could have used S and S. You get a matrix A the same way. You could have used T and T for both sides. You get the matrix A. Remember how you get the matrix A? It's the same thing. Okay, that's the matrix A. How did you get the matrix A? First find L on each of these and use the basis on the right to find the coordinate vectors. Those coordinate vectors get you A. So the point is, why did I choose S for left and T for right? The two spaces are the same. I could have used S for left and S for right, or T for left and T for right. You would get different matrices. That's all we are saying. Okay. S for left, and S for right. You get A. T for left, T for right. You get another matrix A. So notice all these different matrices are different, but the eigenvalues will be the same. The point is, eigenvalue is not as dependent on the matrix as it is on the linear transformation. In each case, we can look for eigenvalues. L of x equals A times x. Now this is very important. If lambda is a scalar, real or complex, x is such that Ax equals lambda x. That's what a eigenvalue is. What does that mean? Lambda is called eigenvalue of A. X is called associated eigenvector. Okay. How do you identify eigenvalues without guessing? So far we have been guessing. So here comes the crux. Let's continue in the next video.